start to read the problems, whether or not we have an electrolyte. We'll deal with the electrolyte problem towards the end of the chapter. This is freezing point depression. Following behind it, same form of the equation. Boiling point elevation. Same thing. You have delta T, the change in the boiling point. The molality of the solution, K sub B in this case, instead of your solvent will change when you add a solute. You have the original smaller fraction, you have the original pressure, and you will get a vapor pressure lower with the addition of a solute. The caveat that is tucked behind that is that the solute that you're adding is not volatile. If your solvent and your solute are both volatile, but Raoult's law gets changed a little bit. For example, we would say that the solute vapor pressure would have its own pressure as well as a solvent. So they both add to the vapor pressure that you'll be experiencing above the liquid. So the total pressure is that of the solute and the solvent. That's the big difference. If they tell you in the problem that what you're dealing with has a vapor pressure, they'll say it's, the wording they'll use, it's volatile. So the pressure gets more complicated because we have both the solute and the solvent adding to it. Now, when they become additive, the bottom of 571 shows three cases. There's three things that can happen when you make solutions, and I'll just draw bottom of 571, and I'll do a quick sketch of it. These graphs kind of look the same, but in the first one, what they call the normalized picture, this is what happens if you have an ideal solution. The ideal solution, the two of the species, when they're mixed, perform as we expect them to perform. You get, if we look at this graph, the mole fraction of A, the vapor pressure. These diagrams take a little bit to get used to, but if we look at it, they have these lines crisscrossing. If we look at the first line, when it starts here, goes to this corner. This bottom x-axis is the mole fraction of A. If we look at it on the one side, the mole fraction of A is 0, and on this side it is 1. In other words, if we look at this side, there's none of part A there. It's all A on this side. So it spans a whole different bunch of mole fractions. Conversely, you have the second red line crisscrosses. We have these two crisscrossing. The line that we're really going to worry about, irrespective of these two, is the line, and it's not going to be perfectly drawn, that connects the two. This line here is the one that we're worried about, the shape of that one. That line is the vapor pressure of the solution. if that line, and it shows it pretty nice there, is of a form that takes a linear path from part A to part B, linear path. It's called an ideal solution. The vapor pressure of the two of them mixing together is exactly what we expect it to be. There's no interferences that are going on between them. They're both a bit volatile, but they're additive in the vapor pressure that they show. Their diagram has it on more of a slant, but if we look at it, it's a linear path across. If you look at the other two examples there, they have the same crisscrossing of A and B, but what happens is, in this second one, if you notice, the line dips, one of them dips down, one of them, the line bows outward. That's what we're worried about. When you have the line bowing downward, this downward deflection you see here, it says that the vapor pressure of this solution right here is less than what it was predicted to be. We thought it would be a nice straight linear line across, that the two would be additive. The fact here, they get this difference here. We get a lower vapor pressure for our solution than we predicted. It's not ideal, and we're getting an issue. The key is to figure out what the issue is. The issue here is that when we make a solution, what do? We break the solute apart, we break the solvent apart. And then the two, solvent and solute, make the solution. When you see a lower vapor pressure here of the solution, it tells you that there's strong solute and solvent forces. That the solution you made, those two pieces, the solute and solvent, like each other so much that they stick together that the resulting vapor pressure is less than we thought it would be. It's not readily going to become a vapor. They actually like each other and they stick together. In that case, they say strong solute-solvent interactions. You see that bowing inward of the data. In this case, the vapor pressure is lower than what we would have predicted it to be. If we thought it was going to be 500, we're seeing 400. Reason being, solute and solvent like each other quite a bit. They're sticking together more. They're not releasing into the atmosphere. Conversely, if we see this case where the vapor pressure that we're seeing is higher in the solution, the opposite is the case. If we predicted a vapor pressure of, say, 500, but now we're getting vapor pressures of 600, 700, although the solution has been made, the particles, the solvent and the solute particles, have weak interactions. We predicted in both of these, in all three of these cases, this is where the solute has a volatility to it. And we should see a linear dependence. You should be able to say, so much of A, so much of B, I get this is the ideal pressure that I should develop. If we see lower than that, that means the solute and the solvent really like each other. If it doesn't, it means the interaction of the solute and solvent is weak. They're not as tucked together as we thought they should be. If we look at an example of this, the example comes from another textbook, but I'm going to show you how this, what this looks like. Let's take a look at the following. We have a solution. A mixture. And I have to tell us two volatile solutions. We have in one mole of benzene. Benzene is C6H6 mixed with 2 moles toluene. toluene is C7H8. What we're going to do is we're going to find out and look at. Both of these species have their own vapor pressure. So as part of the problem, the data that would come with the problem, benzene's vapor pressure, 75 torr. Toluene's vapor pressure, 22 torrs. We can see before we even get into the problem, benzene has a much higher vapor pressure. And that will be shown when we actually start to do the calculation. We're going to calculate the vapor pressure for the benzene. We're going to calculate the vapor pressure of the toluene. We're going to find the total vapor pressure. And then we're going to look at the mole fraction of the benzene in the vapor. I'll show you how we do each part of that. So we're going to find the individual vapor pressures, the total they add up to, and then I want to find out how much of the benzene is actually in the vapor. Not in the solution, it's actually escaping from the material. Let's go one by one. Find the vapor pressure of the benzene. We'll call that P sub B, the vapor pressure of the benzene. It will be equal to the mole fraction of the benzene multiplied by whatever the vapor pressure of pure benzene is. If we look at our system here, we have to find what the vapor pressures are of the benzene and the toluene. You can see that the solution has 1 mole of benzene to 2 moles of toluene, total 3 moles. So if we look at this, mole fraction of benzene, 1 mole divided by the total of the 3 moles of both the benzene and the toluene. So a mole fraction of benzene in this case is a third, 0.33. So if we take that, it tells us that pressure of the benzene is 75. Pressure of the benzene above the liquid is about 25 to 1. First thing we're looking for, pressure of the benzene. We do the exact same calculation.
How did you get the 3 moles as the total?
Yep, 3 is that we have 1 mole with 2 mole together.
Okay.
All